Hi everyone. Today we are going to discuss the basics of Newton's method. We will learn about the main ideas and some theoretical results on its convergence rate. Here are some additional reading materials if you would like to learn more about the details. First, we will discuss how to use Newton's method to find the root of a function. Then we will investigate how to use it for function minimization. After that, we will see how Newton's method can be motivated by quadratic approximation and what kind of convergence rates we can achieve with this method. We will also show that the convergence behavior of Newton's method can be quite complicated, and it can often lead to beautiful but intricate fractals. Newton's method was originally not designed for minimization, but instead to find the roots of functions. This method is also known as the Newton-Raphson method. Let phi be a function that maps real numbers to real numbers. Assume that at some point x star, we have phi of x star equals 0. The question is, how can we find x star? Before going into the details, let's briefly review the history of how Newton's method was developed. This was probably one of the first applications of Newton's method. It's based on the simple update rule, xn plus 1 equals 1/2 times xn plus s over xn. We will see that this is a special case of Newton's method. If we define the function f of x equals x squared minus s, then Newton's method tries to find the root of this function, that is a value x, such that x squared equals s. In other words, this update rule attempts to compute the square root of s. For example, let s be set to 100. Let's try different starting values for this update rule. We will look at how the update behaves when we start from x0 equals 50, x0 equals 1, and x0 equals minus 5. This figure shows the convergence of Newton's method for all these three starting points. As you can see, when x0 is 1 or x0 is 50, Newton's method converges to 10, which is indeed the square root of 100. When x0 is minus 5, the method converges to minus 10, which is also valid since minus 10 is also a square root of 100. Newton is believed to have first developed this method around 1669. However, his work was somewhat complicated and was not published until 1711. Before Newton's results were published, in 1690, Joseph Robson developed a simpler method for finding roots of polynomials. This is why the method is often called the Newton-Raphson method. In 1740, Simpson described it as an iterative method for solving general nonlinear equations and showed how to use it for optimization problems. So, interestingly, it seems that Newton himself never applied his method to optimization. In 1879, Cayley further generalized the method to complex functions and complex roots. After this introduction, let's begin discussing the motivation behind the derivation of Newton's method. Let phi be a function mapping real numbers to real numbers. Assume that phi of x star equals 0, and our goal is to find x star. Let's take a first-order Taylor series approximation of phi around the point x. We obtain phi at x plus delta x equals phi of x plus the derivative of phi of x times delta x plus a small remaining term. Now suppose we move from x by an amount delta x and arrive at x star. So x plus delta x equals x star. The remaining higher order term in the Taylor expansion is small and will be ignored. Since x star is the root, we have phi of x star equals 0. Therefore, we obtain phi of x plus the derivative of phi of x times delta x is approximately 0. Solving this equation for delta x, we get that delta x equals minus phi of x divided by the derivative of phi at x. Now let's use this update iteratively. Starting from a point xk, we move by delta x and arrive at a new point xk plus 1. We have that xk plus 1 equals xk plus delta x, which is xk minus phi of xk divided by the derivative of phi at xk. Newton's method can be illustrated using the following picture. Using a Taylor series expression, we approximate the function as f hat x equals f of x0 plus the derivative of f at x0 times x minus x0. Let this point be x0. We approximate the function f by its first order Taylor expansion at x0. This approximation is a straight line that's tangent to f at x0. Since finding where the function f equals 0 can be difficult, we instead find where its linear approximation is 0. Because this approximation is a straight line, this is easy to compute. We then move to this new point x1, and from there we repeat the procedure. In the next step, we linearize the function at x1, compute x2, and continue in this way. Here, I'm showing the same process in this animation. First, we calculate x1, then linearize our function in x1, then calculate x2, linearize in x2, and so on till we converge. This process can be generalized to multivariate functions. Let f be a function mapping from an n-dimensional space to an m-dimensional space. We want to find x star such that f of x star is the 0 vector. Starting from a point x, we move by an increment delta x and assume we arrive at x star. Let's again use a first order Taylor expansion, now in the multivariate case, around x. This gives f at x plus delta x equals f of x plus the derivative of f at x times delta x plus the remaining term. Note that the derivative of f is now an m times n dimensional matrix. Delta x is an n-dimensional vector. As before, we will ignore the higher order remaining term. Therefore, f of x plus the derivative of f at x times delta x equals the m-dimensional 0 vector. We can solve this equation for delta x to obtain delta x equals minus the inverse of the derivative of f at x times f of x. If this Jacobian matrix is not invertible, we can use its pseudo-inverse instead. We define delta x to be xk plus 1 minus xk. Therefore, the recursive update rule becomes xk plus 1 equals xk minus the inverse of the derivative matrix times f of xk. This completes the derivation of Newton's method for finding the root of a function. We start from an initial point x0 and iteratively apply this update rule. Now we will discuss how to use Newton's method for function optimization. Let f be a function mapping from n-dimensional vectors to one-dimensional real numbers. Assume that f is twice differentiable. Our goal is to minimize function f. Previously, when we wanted to find the root of a function f, we used this system. F of x plus the derivative of f at x times delta x equals 0. This is known as the Newton system. To minimize a differentiable function f, we need to find the roots of its gradient. This condition may also yield local maxima or saddle points, not just local minima. Here, the gradient function maps from n-dimensional vectors to n-dimensional vectors. The Newton system in this setting becomes this equation, the gradient of f plus the second derivative of f times delta x equals 0. We need to solve this for delta x, which is called the Newton step. Thus, the Newton step is given by delta x equals minus the inverse of the Hessian times the gradient of f. Setting xk plus 1 minus xk equals delta x, we obtain the recursive update rule for minimizing f. As discussed, the Newton step is given by this equation. From this, we obtain xk plus 1 equals xk minus the inverse of the Hessian times the first derivative of function f. This is the update rule of Newton's method for optimizing a function. To run Newton's method, we simply iterate this update until convergence or until a maximum number of iterations is reached. Note that at this point, we don't have any guarantees of convergence. The algorithm may diverge, get stuck in cycles, or if we are not careful, it might even encounter division by 0 during the updates. So how good is this Newton method? This lemma states that as long as the Hessian matrix is strictly positive definite, Newton method provides a decent direction. The proof of this lemma is very simple. We know that if a vector has a negative inner product with the gradient, then it's a decent direction. We also know that the Newton step is given by delta x equals minus the inverse of the Hessian times the first derivative of function f. Since the Hessian is strictly positive definite by assumption, it follows that the inner product between the Newton step and the gradient is negative. Therefore, the Newton step is indeed a decent direction. Let us continue and discuss some other important properties of Newton's method. Under certain conditions, Newton's method can achieve quadratic convergence in the neighborhood of a strict local minimum. On the positive side, this is very fast, much faster than the gradient-based optimization methods we discussed earlier. On the negative side, Newton's method can break down if the Hessian is degenerate. Since we need to compute the inverse of the Hessian, the method may fail if the inverse doesn't exist. Newton's method can also diverge instead of converging to a local minimum. It can get trapped in a loop, or it may even converge to a cycle. When we derived Newton's method for finding the root of a function, we used a first-order Taylor expansion. Now we will derive Newton's method for optimization using a second-order Taylor expansion. Let f be a twice differentiable function mapping from n-dimensional vectors to one-dimensional reals. Let's approximate the function f using its second-order Taylor expansion around xk and denote this approximation by phi of x. Assume that the Hessian at xk is strictly positive definite. This implies that the quadratic approximation phi of x has a unique global minimum. Let xk plus 1 be the global minimizer of the quadratic function phi. Then the gradient of phi at xk plus 1 is the 0 vector. Since phi is a quadratic function, we can easily compute its gradient. It's given by the gradient of f at xk plus the Hessian at xk multiplied by xk plus 1 minus xk. The Newton step is xk plus 1 minus xk, and we can see that it is equal to the negative inverse of the Hessian multiplied by the gradient. Rearranging these terms, we obtain the update rule of Newton's method. It's quite easy to visualize Newton's method for these optimization problems. Assume that we want to minimize a function f and let f hat denotes its second-order Taylor approximation. We start the next iterate of Newton's method from the point x, and the function value here is f of x. We are currently at point x, and in the next iteration, Newton's method moves us to the global minimizer of f hat, that is the second order Taylor approximation of f. The vector between these 2 points is delta x, called the Newton step. After taking the Newton step from point x, we move to x plus delta x, and the function value at this new point is f at x plus delta x. This quadratic approximation is accurate when x is close to the minimum point. Finally, we are ready to investigate the convergence rate of Newton's method. We will start with a simple one-dimensional case and later consider the more general higher dimensional setting. Our goal is to find x star such that f of x star equals 0. We assume that f maps from one-dimensional real numbers to one-dimensional real numbers. Assume also that f has a continuous second derivative at x star. By Taylor's theorem, for some psi n between xn and x star, we have that f of x star equals f of xn plus the derivative of f at xn times x star minus xn plus 1/2 times the second derivative of f at psi n times x star minus xn squared. This last term is the remainder in the Taylor expansion. By Newton's update rule, xn plus 1 equals xn minus f of xn divided by the derivative of f at xn. As discussed earlier, we also have this Taylor expansion. Assuming that the derivative of f at xn is not 0, we can multiply both sides of the Taylor expansion by the inverse of the derivative of f at xn. By rearranging the terms, we obtain the desired expression. Let us now denote the error by epsilon n, and epsilon n equals x star minus xn. Using Newton's update rule, we can express the next error term as epsilon n plus 1 equals x star minus xn plus 1. The update rule for the error becomes epsilon n plus 1 equals minus 1/2 times the inverse of the derivative of f at xn times the second derivative of f at psi n times epsilon n squared. Thus, we have established a relationship between epsilon n plus 1 and epsilon n squared. Let m denote the supremum of the absolute value of the multiplier of epsilon n squared and assume that m is finite. Then we have this bound epsilon n plus 1 in absolute value is less or equal than m times epsilon n squared. Assume also that the initial point is sufficiently close to x star, that is, the absolute value of x star minus x0 is upper bounded by 1/2m. Then it follows that the absolute value of epsilon 1 can be upper bounded by m times 1/2m squared, which is 1/4m. Similarly, epsilon 2 can also be upper bounded. We can see that epsilon n converges to 0, and moreover, the convergence rate is quadratic, according to the definition of quadratic convergence that we discussed at the beginning of the semester. We have seen that under certain conditions, Newton's method can achieve quadratic convergence, at least in one dimension. Now, let's examine some problematic cases where these conditions do not hold and see what kind of convergence behavior we can obtain. First, consider the example where f of x is a third-order polynomial. Our goal is to find the roots of this polynomial. In this case, you can verify that the roots are -3, 1, and 4. Starting from this number, the method converges to 4. Starting from a tiny bit different number, the method converges to -3. Starting from almost the same number, the method converges again to 4. Starting from a little bit different number, the method converges to -3. Then, starting from a tiny bit different number again, the method converges to 1. This behavior is quite chaotic. Even a tiny change in the starting point can lead to convergence to completely different roots. In the next example, let f of x be this third-order polynomial. Our goal is to find its roots. If we start Newton's method from x0 equals 0, then in the next iteration we obtain x1 equals 1, and then x2 equals 0 again, and then x3 equals 1 again. And the method continues cycling between these 2 points forever. Therefore, in this case, Newton's method fails to find a root. This shows that the choice of the starting point is very important. We can illustrate this behavior in the following figure. The black curve represents the function f. If we start Newton's method at x0 equals 0, the blue line shows the first-order Taylor approximation at this point. This line crosses 0 at x equals 1. When x1 is 1, the red line represents the new Taylor approximation. This line crosses 0 at x equals 0, so x2 is 0. Thus, we return to the starting point and get stuck in a cycle. Here is another example where f of x equals x to the power of 1/3. We can compute its derivative, which is given by this function. The second derivative can also be calculated. Now we can see that the supremum of the ratio of the second derivative of f divided by the first derivative of f is infinite. In the convergence theorem we proved earlier, this quantity needed to be bounded. Since this condition doesn't hold, Newton's method may diverge, and indeed this is what happens. Using the derivatives, we can compute the Newton update rule. In this case, it becomes xn plus 1 equals minus 2 times xn. This implies that unless we start exactly at x equals 0, the Newton's method will diverge. Next, we show an example where Newton's method converges to the correct solution, but only at a linear rate rather than a quadratic rate. Let f of x be x squared. We can easily compute its derivatives. The first derivative equals 2x, and the second derivative is 2. We can also see that the supremum of the ratio of the second derivative of f divided by the first derivative of f is infinite, so our convergence theorem doesn't apply. If we compute the Newton update, we obtain xn plus 1 equals xn divided by 2. With this update, starting from any point, we converge to the correct root 0, but the convergence is only linear. Let's look at one more example where f of x equals 7 times x minus log x. This graph shows the function, and you can easily verify that its minimum is attained at x equals 1 over 7. We can compute the derivative of f, and it's simply 7 minus 1 over x. The second derivative is 1 over x squared. The ratio of the first and second derivatives is 7 times x squared minus x. Therefore, the Newton update rule becomes xk plus 1 equals 2 times xk minus 7 xk squared. This table shows the behavior of Newton's method for different starting points. If we start from x0 equals 1, then x1 equals minus 5, x2 equals minus 185, and the method very quickly diverges. If x0 equals 0, then x1 equals 0, x2 equals 0, and the method doesn't move at all. If x0 is 0.1, we converge to the correct solution, and similarly for x0 equals 0.01. In fact, in this example, Newton's method converges to the correct minimum only when the starting point x0 lies between 0 and 2/7. This is the basic form of Newton's method, but it has several generalizations. We have discussed Newton's method in finite dimensional Euclidean spaces, but it can also be extended to infinite dimensional function spaces. There are also variants for optimization on curved manifolds, where each update is constrained to remain on the manifold. Finally, Newton's method can also be generalized to complex valued functions. As we discussed, Newton's method is very sensitive to the starting point, and this behavior often leads to fractal structures. We will now explore this phenomenon. The starting point is important in gradient descent too. As you can see on this surface, depending on where we start, gradient descent might converge to different local minima. However, this behavior is even more complex for Newton's method. Let fz be a fourth-order polynomial, fz equals z to the power of 4 minus 1. Assume that z can be a complex number. The roots of this polynomial are -1, 1, I, and -I. Our goal is to find the roots of f. To visualize what happens when we apply Newton's method, we color each starting point according to which root the method converges to. Here are the results. We use 4 different colors: yellow for convergence to 1, red for convergence to -1, blue for convergence to I, and green for convergence to -I. You can clearly see that the boundaries between these regions are highly intricate and form a fractal structure. Here is another version of the same experiment, but now the colors indicate the number of the iterations required for convergence. Let me show you another example. Here the function f is more complicated, but again we observe an interesting fractal structure. In this example, we chose a polynomial with roots at I, -2.3, and 2.3. Now you can even observe regions where Newton's method does not converge, but instead it keeps jumping around and gets stuck in a cycle. These regions are colored black. As we have seen, Newton's method can be very fast, but it's also very sensitive and may fail to converge. One issue is that the method can take steps that are too large. Several techniques have been proposed to improve the convergence properties of Newton's method. Two of the most popular ways are called the line search method and the damped Newton method. Here we introduce a step size parameter hk, which we choose carefully to improve convergence. Initially, this step size can be set to 1, and if it turns out to be too large, then we can reduce it. Finally, we will discuss a theorem that, under certain conditions, guarantees the convergence of Newton's method in finite dimensional vector spaces. We make the following assumptions. We assume that the second derivative of function f is Lipschitz continuous with a capital L Lipschitz constant. We also assume that x star is a local minimum of function f. At this point, the Hessian of function f is positive semi-definite. Moreover, we assume that the Hessian is lower bounded by lowercase l times identity matrix, where this lowercase l is a strictly positive number. In other words, the function f is locally L strongly convex at x star. We also assume that the initial point x0 is sufficiently close to x star. Formally, we will assume that the norm of x0 minus x star is upper bounded by 2 times lowercase l divided by 3 times capital L. This assumption implies that we are only proving a local convergence result. Finally, we will use the standard Newton update in each iteration. Under these assumptions, the following theorem holds. The norm of xk minus x star is upper bounded by the norm of x0 minus x star for all k. That is, the error at iteration k is never larger than the initial error. We can also prove that the norm of xk plus 1 minus x star is upper bounded by the norm of xk minus x star. And finally, we can also prove that the norm of xk plus 1 minus x star is upper bounded by a constant times xk minus x star squared norm. The second claim shows that the error doesn't increase across iterations, and the third claim establishes a quadratic convergence rate. The proof of this theorem is provided in the appendix. To summarize, we discussed how to use Newton's method to find the roots of functions and how to apply it to unconstrained minimization. We showed that under suitable conditions, Newton's method achieves a quadratic convergence rate, which is much faster than the convergence rate of those methods that we discussed earlier during the semester. At the same time, we also saw that Newton's method can be highly sensitive to the starting point, and this sensitivity can lead to complex and even chaotic behavior, such as Newton fractals. Thank you for your attention. If you have any questions, please let me know.